fairly easy place to live. So if you're interested in, or if you know any students who are interested in doing some study, then, you know, yeah, come and talk to me. I noticed the comments, it's good coffee. I have to say that could be because we've been on lockdown for so much of last year. My criteria for when I'd go back into the office was when we finally had coffee available again.
Probably it's Italian coffee.
Yeah, well, it's South American.
There is a bigger community.
It's really the good one. It's the Italians brought the coffee to Melbourne, I think. But yeah, these days all the good coffee is South American, so it's probably from Brazil anyway.
Yes, the best coffee comes from Brazil, but maybe Italian makes better.
Yeah. It's true. But you know, just to be provocative to Massimo, I have to say I've had better coffee in Melbourne than I've had in Italy. So you can make of that what you will. Anyway, so let's move on. That was kind of the good news, because today I'm talking about the situation on manifolds, and the situation on manifolds is there's almost everything's really open, and there's a lot to be done here. And it seems like such a very natural geometric problem, but you know, I think it's kind of quite subtle and we don't really understand what's going on. So what I'm going to do today is just tell you about what we do know, and then give you some counterexamples to motivate that things are kind of a bit funny. Okay, so let's just recall what we know from flat domains. So this is sorry, I'm having huge technical problems here. Just okay. So on a flat and convex domain, well, if we look just at the eigenvalue problem, with Dirichlet boundary conditions, then we have U is log concave. And so that's nice, but we can also extend this to a wider collection of right-hand sides here, sort of some fairly general functions B here, with some conditions. And B, so B has to be decreasing in the first and third variables and jointly concave in the first two. Sorry, just wanted to. So that's the flat case. So what happens? Oh, and I should also mention that we can also extend this. So all throughout here, I'm taking some really nice results and sort of reducing them to their most simple, basic version with just, you know, Laplacians instead of general elliptic operators and so on. So I should sort of caution that the story doesn't stop with what I'm actually showing you here. again under some sort of natural conditions on F here. So the situation on manifolds, it's pretty open. So what I'm going to do is I'm going to give you one case where we do know something, and that's the case when we have a really symmetric domain. And the case of positive curvature, but only constant curvature, where we also have some results. And then I'll give you some negative results in negative curvature. So let's start. And this is the setup. So we're going to start with highly symmetric domains. And by that, I mean domains with rotational symmetry and a warp product metric. So here we have M, which is kind of like polar coordinates. And we have a metric which looks like this. So here, sigma here is the warping factor. Okay, so for flat space, sigma is just equal to R, and for the sphere, and it's equal to sine of R, and the hyperbolic space, it's equal to sine of R. But the main thing is that we have sigma of naught is equal to naught, and sigma prime of naught is equal to 1. And we consider the ball of radius R. Okay, so the reason why we consider this is, of course, because once we've done this, everything becomes just a question about ODEs. So these sort of symmetric domains, they're kind of good for generating examples and maybe counterexamples, but they're kind of frustrating in that because you've just assumed so much symmetry, you are not really saying much about the general case. So let's write down a theorem. So this is a recent theorem of Shiga. Let me just spell his name correctly. Shiga Solani and Takatsu. And I think this is just on the archive. And what they find is that, say for the eigenvalue problem, here, but also for more general cases, we have, under the condition that the warping factor satisfies, well, is log concave itself, then U is log concave. Okay, so I should say something about this condition here. So, or actually before I say something about that condition, just just observe here that because this is all rotationally symmetric and we have a domain which is also rotationally symmetric, we get quasi-concavity for free. I mean, all the level sets are going to be just circles or spheres. So we're giving away a lot by setting it up in this way. Or not giving away a lot, we're getting it for free. But that's okay. That's what we can do. So this condition here is always satisfied in positive sectional curvature. It's always satisfied in flat case. There it's just like 1 on r squared, minus 1 on r squared. And it's not always satisfied in hyperbolics, in negatively curved cases, but it is in hyperbolic space. But you can certainly cook up some warping factors that don't satisfy this. So let's prove that. So since U is rotationally symmetric, U is just a function of R. So we can write down an ODE for U here. So we have something like this. And we have boundary conditions like that. And we can do the usual thing of writing down log of U. And let me write it down like this. Okay, so all we need to show now is that W is concave. So this just takes us, I guess, 3 steps. The first is to observe that in the center of the domain near 0, then W is concave. And the reason for this is that if we look at our expression for W prime prime, and particularly look at this part here, well, because we've assumed that sigma of naught is equal to naught and sigma prime at naught is equal to 1, this term here is approaching 1 on R. And so this whole term here is like a W prime prime term. So we have okay, so if we put it back, if we replace this by W prime prime, we notice that these all cancel out except for these n's, and we find that this equation, which I'll call, let's call this equation A, becomes n W prime prime is equal to minus lambda minus W prime squared, which is less than 0, so near 0. Okay, so we start off well. Now we just have to make sure that that is maintained for the whole domain. So the next step is to show that W prime is less than 0 on 0R. And this is a sort of very classic ODE argument. If not, there exists some R naught where there's the first point where W prime is equal to 0. Okay, and so the picture of our function here will look like something like this. Let me just draw W prime. So we've started off at W prime of W prime of naught is equal to naught, and we are supposing that there's some point where it comes back to naught here. And so this means that W prime prime has to be positive or non-negative. But if we scroll back a bit and recall what our equation for W prime prime was, let me write it down again. This is equal to minus n minus 1 log sigma prime W prime minus lambda minus W prime squared. And because we are assuming this means that this is going to 0, this is going to 0, so this is equal to minus lambda. And lambda is always positive, and so this is a contradiction. Okay, so we get our result. So I just mentioned there that lambda's always positive. I should mention that this, for those of you who haven't encountered this before, the spectral theory for the on manifolds is sort of in the sort of coarse sense very similar to the theory on flat space. You know, we can set up our sequence of eigenvalues, and the eigenvalues satisfy or are critical points of a Rayleigh quotient, so they have a variational structure, and the first one's always simple and positive. So So that's why I'm just kind of casually saying that lambda is going to be positive. So the final step is to do the same thing to prove that W prime is less than 0. Now W prime, because of step 1 is negative at 0, so it starts off okay. And again, we can just make this little ODE argument, which is that if W prime of some point R naught is equal to 0, and this is the first, has to be the first point, or the smallest point where it's equal to 0, then W, the derivative of that, so the third derivative, has to be non-negative. But if we differentiate our equation for W, then we're going to get an n minus 1 log sigma prime W prime minus an n minus 1 log sigma prime W prime. And then we have a lambda term now that just drops out, and then we have a derivative of W prime squared. Okay, so at R naught, we can first off, we've assumed that this will be 0. We've shown that W prime will be less than 0, and our assumption is that this second derivative of log sigma is going to be negative. So this is all going to be negative. So again, we get a contradiction. And so then we're done, because we have the concavity of W is equal to log U. So that's somehow, in some senses, the state of the art for these questions. Although, I mean, looking at this ODE, I think probably or possibly there might be some ways of extending or finding a more general condition here than this one here. So yeah, maybe is there any questions about what's going on there? Okay, so let's move on to domains without such restricted shape. Okay, so let's look in the case of positive curvature. Okay, so for varying curvature, I don't know anything. Pretty much, I couldn't find any results on it. But for constant curvature, so for domains in a sphere, we do have some results. So let me mention those. Okay, so So we start off with a convex domain in Sn. And here we should be careful because the domain has to stay inside a hemisphere. Because if we have a domain that comes out of a hemisphere, then it will no longer be convex. Because you could find a shorter geodesic that was completely outside your domain. So we're sort of thinking about things that are something like this. Oh, look, let's do an ad for this lecture series. Must be inside B minus. Well, it's not really B minus. I guess it's Sn minus. Close. Okay, so then so a quite old result is that the Braskamp-Lieb result holds is that the first eigenfunction, Dirichlet eigenfunction, is log concave. And I don't know what the earliest result here is. I found something from Li and Wang in 87, and their paper is really short, and it just sort of consists of saying, the proof from the Yao proof that I mentioned on, I think it was Tuesday or Wednesday. That one actually holds in this situation. But I feel like it should go back further. I also wanted to mention that my friend Guofeng Wei and collaborators in a series of papers over the last 3 or 4 years. They found that you can do a modulus of continuity result, and so this 2-point result, and pen keeps just stopping, and the only way to fix it that I know about is to take the battery out. So they found a modulus of concavity result showing what we call quantitative concavity estimates. And they were able to make exactly the method that we saw last time work in this geometric setting. The extension is not trivial because things become a lot complicated once you have to deal with the curvature. And it would become unimaginably more complicated if you had non-constant curvature, because then you would end up with all these derivatives of curvature terms, which seems quite impossible at the moment. And they also very strongly use that the curvature is positive, and the proof really does not work if curvature is negative. So that's all really nice. Something that's also very recent, which I wanted to mention to you, is a very recent paper for not the eigenvalue case, but the sort of general elliptic equations. And this is another recent result. So again, we've got a convex domain in the sphere. This is a theorem of Matt Langford and Julian Scheuer from last year. And the idea is you have a solution to some elliptic equation like this, and again, you know, I'm watering down the result here. So I'll just write more general operators possible. And the reason why I'm not writing down the more general operators in this case is because to write down the conditions of what you need on these operators, it's quite precise. But we can write down the conditions we need for B. Which are the same conditions that we had under the this midpoint concavity proof before. So B's decreasing in the third variable, jointly concave in the first two, and decreasing in the second variable. And just to allow for the most general kind of equations here and solutions, they just give a condition on the boundary, which you can show that is satisfied in fairly natural conditions, which is that and I'm going to write gamma. Okay, I'm going to write something here and then I'll say what it means. But the conclusion is under these conditions, U is concave. Okay, so the idea is that we'd apply this to log of the first eigenfunction, which will satisfy something of this form, and then get the log concavity result. Now, what's going on here? Okay, so this result is really just a very, very literal extension of the midpoint concavity result that we talked about before. And do you remember that we just sort of defined this function which detects concavity, or by saying well, this is what we read before. I'm going to rub it out. Okay, that's what we had before in a flat domain. Now on a curved domain, we can't necessarily add these terms together. So what we do is our domain will look something like this, and then we take for any 2 points which are on the domain, we just take the geodesic that goes between them. So this is the geodesic. So we take this to be like gamma of -1. We call this gamma of 1. And then we just have the point gamma of 0, which is the midpoint. So we just replace all these terms in here. This will be gamma xy of 0. This will be gamma of -1. And this one will be gamma of 1. And now we can do exactly what we did with that proof before. We can try and show that this function here is always positive. We start off by assuming that that has a minimum, and we show that minimum is always going to be positive. But we should be super careful here, because now what we have to do when we start taking derivatives, we have to take derivatives of these geodesics. And so we need to define Jacobi field. And once we do that, and that's where we'll pick up the curvature terms, which have to have the right sign. So there's some nice kind of analysis using Jacobi fields there. And also, again, we everything's simplified by the assumption that the curvature is constant. So that's something else that's also very, very fresh and seems like the best we can do at the moment. Is there any questions so far?
Julie, sorry,
yeah.
But what do you mean by curvature? You speak about mean curvature or Gaussian curvature?
About the domain?
Yes, about when you speak about the positive curvature, for example.
So here I'm just working in constant curvature domain. So this is just saying the domain is a sphere.
Okay, okay.
It's
So
really,
it doesn't matter. Okay.
Yeah, I'm sorry, it's so restrictive. Yeah. Yeah, previously for the ball one, the sectional curvature was okay, but everything is fairly rigid there as well. Yeah, and so when I talk about concavity on a function on a manifold here, it's concavity you can think about as satisfying this condition here or some other. It's just like the previous concavity, except you always take the points along a geodesic. Yeah, so let's let's move on to negative constant curvature, so hyperbolic space. Oh, here we go. And so again, let's consider the eigenvalue problem. So we've got some domain and it's convex. So convex in the sense of geodesics. So same kind of setup. And so the problem is that there exists, let me just write this as a fact, there exists domains omega with U is not concave, and not concave in any sense, like it's not log concave, it's not even quasi concave. So let me just write. So there's level sets that, or super level sets that are not convex. So this is kind of really interesting. So I'm going to kind of describe how you can construct such domains here. So originally this is first noticed by Xi in 89. And he constructed a really nice little domain where you could show that the level sets had sort of a dint. So last year we managed to construct this sort of dramatically terrible domain in which your level sets are not even connected and your eigenfunction can have two peaks. So let me describe this to you. This is an example which I constructed with Theodora Borny and Hien Nguyen. And Alina Stanku and Guofeng Wei and Valentina Wheeler. And we use a setup that starts off being pretty similar to Xi's. So we're going to work in H2. And on H2, we use a Poincare disk model. Not a Poincare disk model, sorry, the Poincare half plane. And so on this half plane, we have a metric which is given by dx squared plus dy squared divided by y squared. So as you go further up here, everything gets warped. And Okay, so I'm going to put coordinates on this one given by theta, like this, and r. So we've got theta. So this is theta equals 0 up here. And on this, oh no, first I'm going to draw the domain. So in this setup, the geodesics are sort of semicircles centered on the x-axis, or their vertical lines. And so I'm going to set up a domain which is given by geodesics here. And then kind of radial sections there. So this is omega. And we can write down omega. It's given by so r runs between, say, 1 and some constant, which for reasons will be given by this. So mu here is just a constant, which I'm actually going to choose very large. So my domain here sort of is going to shrink down to something very narrow. And theta is just some symmetric choice here. And so the point about this is that it's geodesically convex because, well, we can draw some geodesics in there, because this is a geodesic there, and this is a geodesic here. And on this part here, we have geodesics which at any point they just sort of touch and glance off. So go like that. There's a geodesics. So this domain is certainly convex. Okay, and because of this setup, we can allow, it has a separation of variables solution. And I'll write that down. So we have u of r theta is equal to some function h of theta alone and some function f of r alone. And we get some ODEs that come out of this, which are kind of pretty simple. Now mu here is something we used before. Let's, oops, let me add a new color. So mu here is this little parameter in my definition of the domain. And so, so if mu's large, then the domain shrinks down to being very thin. And that's what's going to happen. I'm going to choose mu sufficiently large so that the domain becomes thin enough that I get this behavior. So the other ODE is h theta theta plus lambda sec theta squared times h is equal to mu h. And they both satisfy Dirichlet boundary conditions. So they're two ODEs, and they're linked by mu, which is like a separation parameter. And we can solve them. In fact, we can solve this first one directly. So let's call this equation B and equation C. So I can even write it down for you. This is f of r is equal to sine of mu log r. So f looks something like this. And then we start to look at C, and we don't solve this one directly. But what we can show quite easily is that it has a minimum at the center of the domain. Okay, so this one, h, it's a symmetric function because sec is symmetric on this domain. And we start off by claiming that for sufficiently large mu, which depends on L, so L is kind of the length of the domain. Let's go back here. So L is this, 2L is this opening angle. Yeah. So for sufficiently large mu, we have mu is less than lambda. Okay, and then, so this is sort of ODE methods, which are similar to the ODE methods I was talking about in the previous proof. You just show that if you don't have these kind of things, then you get a contradiction, and all quite fun to go through. But the consequence of this is we look at this equation C at theta equals 0. And so there we find that h theta theta is equal to minus sec theta squared h plus mu h. This is always going to be, well, this is going to be 0 at the center. So this is going to be h times mu minus lambda, and this is positive. So when we think about what h looks like, we have 0 boundary values here. So this is at minus L, this is at L, this is at 0. We know h is 0 here, but this is telling us that at the middle here we have a local minimum. So it has to have a minimum here. And so that means that we lose any sort of concavity here. So in fact, we can, by doing quite a bit more work, we can show that if we choose mu appropriately, we can even have an H that kind of just is extremely small in the center here. So it kind of almost, the domain is, or the eigenfunction is kind of splitting the domain into two halves. And once you have two peaks like this, this means that your level sets are going to look something like this. Let's draw that domain again. So you're going to have around those two peaks, they're going to be, completely separated level sets at those heights. And you know that because your domain is convex, towards the boundary, your level sets have to be convex too. So in between, you expect sort of some kind of crazy behavior like this. And then maybe some, not very convex level sets in between. So this was really surprising to us. And I should kind of give you a bit of a heuristic for what's going on there. If we look at our domain here, and we remember that our metric is, it's like dx squared plus dy squared divided by y squared. And this means that this edge here is actually longer than this cross section across here. So even though I've drawn that domain as sort of some nicely curving thing, it's kind of a little bit of a lie. So if we were to draw this domain in the Poincare disk model, the domain would look, so these geodesics would look like this, and then these ends would look like this. So when we draw it like this, you sort of can see that you can, this domain really has something like a neck. Which separates sort of two blobs. And so it allows the eigenfunction to kind of concentrate all its mass in two sort of separate areas. And that's why we get the level sets shaped like this. So yeah, this is a negative result. So let me just finish up by saying that we have some hope that in more restricted, if we make more restricted domains, like something like a stronger curvature condition on the domain, then we might be able to get some concavity results. So it's not really a conjecture, but it's more like a hope. And so a plausible conjecture would be if the domain was what you'd call horoconvex, which means that it would always stay on one side of a horocircle. So it's like a restriction on the, it's sort of saying that the boundary has to be more curved in hyperbolic space. But we don't really know how to approach that. So I guess, I started off with an ad, and this is kind of also an ad, is that there's so many interesting problems when we look at this on manifolds, and really it's open and nothing much has been done. Well, not enough has been done. I shouldn't say nothing's being done, but there's still so many natural questions that we haven't really looked at yet. So on that slightly, I don't know if that's a hopeful note, because there's a lot out there to discover, or a depressing note that we haven't discovered it yet. But I'm going to end there. But maybe, has anyone got any questions?